robin.
Yeah.
Right, yeah, right. So the scheduling as a whole is what ENIAC said, which is, it's a resource allocation, so it's allocating CPU time. What's actually mind-bending about this is that in order to allocate CPU time, the operating system has to allocate time for itself to allocate the time, because it needs the CPU to run, to do its job. So it's like, whoa. So on a single core system, you've obviously got to keep allowing the operating system to have time. If any program manipulates that, then the scheduler can't become active. So it's all about allocating CPU time. But it's to do with processors, so it's process management. Now it depends how many CPUs, because you could, if you've got multiple cores, you could dedicate one core to the operating system, so it's always got a chance to run. But you've still got competing things anyway, because you've got competing devices, input-output resources, memory. You can't all access it all at the same time. So even if you had 50 CPUs running in parallel, they couldn't all be doing this accessing RAM at once. At most, you get dual access RAM. All the double data RAM is like dual access. So yeah, it isn't as simple as just getting loads of CPUs. Right. So the basic thing is to allocate time slices. How we allocate them is the algorithms, the different, and we look at it super superficial. So we got the scheduling algorithms, and obviously these are just like real glossing over. So what methods have we got? And then we'll look at the structure of it all. Right, so the scheduling algorithms. So you said
Round robin.
Round robin. So what is a round robin?
It's when they've got a set amount of CPU time each. So when the algorithms come in, they're ordered, and the first one goes in. Once it's reached its time, it's either finished or it's sent back to the bottom of the queue. The next one moves on.
Right. So it's a queue.
Yeah.
Yeah, it's a queue system. Everyone gets a time slice, or you get everyone gets 2 time slices. You can put priorities in there by having different queues and things like that, or allocating as a process starts. Don't call them algorithms. They call them processes or tasks. At this level, we just think of all those as the same things. Okay, so yeah, as a process asks the operating system for permission to launch, to be loaded up and put onto the queue, the priority is assigned. So it might be a simple system. You can do priority by either giving more time slices, so you let something stay on the CPU longer, or you don't use one queue, you use multiple queues. But yeah, so round robin, yeah, just if you've finished, good, you can get lost. If not, you go on the back and you just keep processing. In a sense. Right, so what are the other ones?
There was a shortest time first and shortest time remaining.
Right, shortest time first. Now, in order to do that, you've got to know something about the application. So you need a log, a history of every time that application's run, how long does it need to run before it completed. So for general programs, that's no good, but for services that are running in the background, you can do that. So if something's got to handshake with a server, that might take a millisecond to run, and you say, right, just get it to the front, let it have a go, because we know it's going to go again, and we don't have to worry about it for 2 seconds or whatever. Remember, you're talking about really, really short time frames. So when we say a time slice, we might mean a millionth of a second of time that the program runs for, but it can get a lot of work done in that time. It is quite scary. So yeah, shortest time remaining is 1. So you might know that you might know that a program or a task takes 5 seconds to run, and it's been running for 4 3/4 seconds. So you will think, I'll just let it run until it's finished. Although that's too long a bit of time, but that's just an example. What was the other one? So it's shortest.
Well, Okay, so the.
So with time remaining, what was the other one? Short is.
Time first. Because like one of them was like
It was total time.
right, because one of them was like ordering it as the shortest program itself went first, but then there was also like if one had been running for quite a while and only had a bit left.
Yeah. So shortest time remaining is that one.
Yeah.
So what are we calling the other one then? The one.
Shortest job first.
Yeah. So yeah, I would say always explain yourself when you're answering questions in case you don't use the exact right word. So yeah, shortest job. So if we know something, so something like a keyboard driver or a mouse driver that needs to interrogate the state of the keyboard or the mouse, generally will operate within a fixed timescale anyway. So the API that the operating system manufacturer gives you for when you're writing drivers, they will say this function of this driver cannot execute more than so many milliseconds. It's got to finish its job. So it might be that the mouse driver's got to execute in under 30 milliseconds. And if you don't write your code well and it goes over, then you're going to screw things up. So yeah, you've got like things. So yeah, the operating system might know, yeah, that one's quick, straight to the front of the queue, get gone. Okay, right, so that's 3.
Isn't there?
Multi-level feedback queues.
Hang on, that's the biggie.
First come, first serve.
Yeah, so there's the first come, first serve, which sounds like a really simple system, but can be some things can never execute. Only suitable for certain. So if you're in a batch system where you're just doing data processing jobs, then a first come, first serve might work, as long as processors aren't repeatedly arriving, saying I want something off you. And then the one that's actually used, or that uses a mixture of all these, is the multi-level feedback queue, which sounds horrendous, but is actually incredibly clever and doesn't need much working out. I don't know why I put dashes in there, but there you go. Got the insight into my brain. I'm going to keep going with that as well. Multi-level feedback queue. Right. Oh, you're going to... Where you going? So, you have a queue. And you put your tasks in that queue. And because it's a queue, where do we remove the tasks from? Front. So a task comes up, gets to go on the CPU, gets its time slice. If it runs to the end of its time slice without being interrupted, and we'll get onto that in a minute, if it runs to the end of its time slice, you say, well, actually, when it got the CPU, it ran, just got on. So it doesn't need to be high priority. So we will drop it down to a lower priority level. So it might be the way that you manage priority is you say, I will take one from the top, every other I will take from here, and then you can have more queues. So if we come off, so this is the high priority, and you can have as many of these levels as you want. Let's say we're just going to do 3. If we come out of the medium level and we get on the CPU and we run to the end, then we go onto the lower priority queue. So we say, like, well, you know, if it gets its CPU time, it runs and does its slice. So it ends up on the low priority. If we pull something from the low priority and it gets interrupted and doesn't get to finish its time slice, then you say, right, well, let's put it back up onto the medium level. And if it runs from the medium level and doesn't get to run to the end of its time slice, then you move it back up. So you're not having to keep metrics, although you are keeping metrics, but you don't have to in order to manage the priority. It's just automatic. Okay? So it's actually quite a clever, simple system that manages priority dynamically for you. So there's no like, oh, I've got to think about it. Which is what you want. You want the operating system, when it's doing its scheduling, to just think about it really in the shortest time possible and decide who gets to go on next. You don't want to be like going, oh, well, you've done this and that, and because that's all going to take time. We want this to be quick. In a single core environment, it's got to be super quick. Right, so in order to understand what we mean by getting to the end of your time slice, we have to look at the general scheduling model. And that is 3 states. We have a ready state. So all the processes, that's where the queues are. You can come out of the ready state to a running state, which is when you've got CPU time. If you get to the end of your time slice, you go back to ready. So that's the end of slice, start of slice. Slice. Oh. Spent too long doing that. Right. You can end up in a blocked state. So you were in the middle of your run on your CPU, and then you made a request, an I/O request, and you can't just sit there on the CPU waiting for a byte to arrive from the network card or some data to arrive from the hard drive. So you make an I/O request, and then immediately the scheduler goes, right, well, that's it. You're getting off the CPU while you're waiting for that. So you sit in a block state waiting for a I/O request to come in. You only leave the block state when you get your I/O request, but you don't go straight back onto the CPU. You go back into the ready. So okay, it might be that you actually, before you get to go on the CPU and you're in the ready state, another thing makes an I/O request for the resource that you've got, but it's of higher priority, so you lose it. And you do get some problems where you can have 2 competing processors that have got hold of a resource each and want the resource the other one's got. So you can, in this block thing, you can get these things called, why have I put get? That's completely the wrong word. Deadly is the word I wanted. You get something called a deadly embrace, where process 1 has got resource A, process 2's got resource B, and process 1 wants resource B, and process 2 wants resource A. And you get this like, well, I'm not giving it up. So you have to get the operating system has to like go, well, I'm nicking it off you, or they can have it. So you get lots of ways in which you will end up in the block state. From the block state, you can actually be killed. You can actually get there if you do something bad as well. So if you misbehave as a process, why are you smirking, man? Why are you smirking? If you misbehave as a process, you do something you shouldn't have done, you like infringe memory and things like that, the operating system can put you in an isolation state. So when you get, then the thing comes up where it says not responding. So if you've got hang, so you've requested something, you're sat there waiting and waiting and waiting, and it's never coming through, so you just remain blocked. It might be the operating system asks the user, which is what you get, this program is not responding. Do you want to wait, or do you want to knock it on the head? To which point you go, knock it on the head, and it goes and kills it. But actually, you can get in the kill state from ready, from the running. So, like Mac said earlier, you said you might get to the end of your time slice and you're finished when you were talking about the round robin. So, like, that's the worst spelling of finished I've ever done. It's finished. You could argue that was still part of the F. And I am going to argue that. Finished. We don't need any more CPU time, so we can go and get killed. Okay, so when we're talking about the multi-level block index, it's if I've gone this way, so you could say drop priority. So priority. If you go this way, you could say increase priority. So basically you end up with two classes of process. You have those that are CPU bound, so they only really need data processing, and you get these ones which we call IO bound. So good examples, if you're doing a mathematical calculation, you're generally going to be CPU bound because you're just using RAM. If you're doing anything that's contacting devices, like you're streaming something or you're communicating over a network, you're going to be IO bound. So really IO bound processors should have higher priority. So the multi-level block index automatically filters for you. Okay. Any questions about scheduling? You're never going to get asked too deep. They'll ask you, the throwaways will be, tell me some scheduling names. They might ask you about them a little bit, but if you can just remember that process model and how the multi-level block index that seems to be something else. That's how databases are structured. The multi-level feedback queue is structured, then you can actually see quite easily from the diagram how it automatically gets filtered for you. Okay.